as the result of our investigation, we should have come up with 3 essential conditions for the continuity of a function at a point. So before I list them out, let's see if we can make sense of that investigation. Let's recap it, shall we? So here's the results that we should have gotten from our table. And what I'm going to suggest that you do is grab a highlighter, pick your favorite color. I'm going to pick green, not because it's my favorite color, but just because I haven't used it yet. And I'm going to highlight all of the ones that I put check marks or yeses by for continuity, right? So I want to see if there's some kind of pattern between all of these things. So all of the ones, really it's in black, right? At least on my copy of it here. So all of these have something in common. I wonder what it is. So obviously, you probably picked up on the fact that all of the ones that are continuous, they had the exact same number all the way across. The function value was the same thing as the value of the limit from the left, the value of the limit from the right, the value of the limit from both sides, and yes, it was continuous. That's the case for each one of those, right? And each one of those, they pretty much tell us what the conditions are for continuity. And there are 3 of them. So this first column here is like our function has to be defined at that point. So for example, let's look at x equals -4. So at x equals -4, we have a vertical asymptote. Our graph's not even defined there. It's not going to be continuous. I'd mark it off the list. So here's our first one here, is that your function has to be defined. Can you even see that? How about now? All right. Now the next one has to do with these 2 columns. So I'm checking my limit from the left side and the right side. All right. Well, almost all of them have some sort of limit that exists. There was one here that, like, we had infinity on both sides, and I know that that doesn't exist. That was because of that asymptote. But then I also had some that it didn't match up. Like this -4 didn't match up with this 1, even though the function was defined at that particular place. It didn't match up. It was different left-right behavior. So when your limit is the same on both sides, regardless of whether or not your function is defined, if your limit's the same on both sides, that means your limit exists. Okay. All right, then. Yeah, the limit exists. Like, for example, the limit exists right here at x equals 1. The limit exists because both of these are 3. And so I can say, hey, the value of the limit there is 3, but that's not enough. Look, there's this red x right there. So why is that the case? Let's come back over here at x equals 1. At x equals 1, yeah, the function's defined there. That's not even it. All right, it's over here. The function's defined there, but the point is up here, which makes it so it's not continuous right there. The value of the point and the value of the limit need to match up. So that's what this last column is showing us, or next to the last column, that this value here has to match up with this value here. That the limit as x approaches a of f of x needs to be equal to f of a. As a matter of fact, this is what we used whenever we were doing this direct substitution of limits to evaluate them. It worked because the function was continuous at that point, so I was allowed to just plug that number in, and it's the same thing as the function value. It's based on the definition of continuity. Okay, then, let's write something down for sure, because this needs to be either tattooed on your arm before you take the AP calculus exam, or, just simply memorized. So we have the continuity of a function at a particular point. A function f is continuous at x equals 3 if all 3 of these conditions are met. All 3 of them. And this is a definition. So when we're applying a definition, we have to hit all 3 key components. The first one is that your function has to be defined. F of a is defined. So if I already know my function's not defined there because there's a little point of discontinuity or there's a vertical asymptote, I'm done. It's not continuous there. The second one is that the limit as x approaches a of f of x has to exist. We have to approach the same number from both sides. It can't be unbounded if there's an asymptote right there. Sure, that's not enough. Nope. And then the last one is that the first one and the second one have to be the same. The value of the limit as x approaches a of f of x has to equal f of a. So sometimes I get from students, well, why isn't the definition of continuity just the last one, just this number 3? Because doesn't this number 3 imply the last two? And technically it does. And the reason why it does is because if you put an equal sign with an f of x number here, this is some unique value you're saying that the limit is equal to, therefore the limit exists, right? And if you put f of a, that implies that f of a is a number that you know that the function's actually defined there. So the reason why we have the other two, though, is think of it as a checklist. I don't want to have to check this part right here. If the function's just not defined, I'm done. I don't have to check any kind of limit, right? And the same thing goes with the second one. Well, maybe the function was defined, but the limit didn't exist there, so I'm done. I don't have to look to see if the value of the limit is equal to the value of the point there. Okay, so in terms of layman terms or whatever, that's what I'm looking for continuity of function at a point, is that the function is defined at that point and the limit at that point is equal to the value of the point. Let's look at this on a pretty simple example. Just illustrate the definition at 3 different points. So use the graph and the definition of continuity to determine whether f is continuous at x equals 1, at 3, and at 5. Well, I already know just by visual inspection whether or not it's continuous. For example, I look at 1. There's a hole right there. There's a point of discontinuity, a hole. It is not continuous, but I want to apply the definition in my wording because sometimes this comes up on the free response section. If it's multiple choice, nobody knows what your reasoning is. But on a free response question, they're looking for you to hit those 3 components in order to justify whether or not the function is continuous or not. So I'm going to apply the definition in that case. 3, I can see very clearly here it's not continuous. There's a big old gap here, right? But again, I need to phrase it in terms of the definition we just wrote down. All right, and then finally, there is, again, a point of discontinuity here, even though the function value is right up there. So here's what I would probably do if I were writing this up. If something like this came up on the AP Calculus exam and it asked me to justify whether or not my function was continuous at any of these points, here's the first one, x equals 1. So why isn't the function continuous at x equals 1? Let's look at our checklist. That first one, is the function actually defined at that point? Nah, there's no like googly eye that fell. That's it, it's done, right? So I'm going to say f of x is not continuous at x equals 1 because f of 1 is not defined. I don't have to hit the other 2 parts of the definition because it already failed the first condition. It's done. Okay, the next one was x equals 3. Okay, so looking at x equals 3, again, going through the little checklist, my checklist, the first one is that the function's defined there. It is because there's a dot. It's a colored in dot. It's defined there. Okay, the next one is, does the limit exist at that point? No, the limit doesn't exist at that point because of differing left-right behavior. The limit does not exist, and that's the reason why it's not continuous there. So I might say in some sort of checklist, you can write it as a checklist, like a bulleted checklist, or you could write it as a sentence. So for example, maybe I model it like a checklist here. So I'm going to say that f of 3 is defined. I know that. Maybe I even say that it is defined as, what? Oh, I can't say it's defined as anything. I don't even know what that number is. So I'm not even going to put that part there. Okay, and then the second one, though, is the limit as x approaches 3 of f of x does not exist due to, well, it's different on both sides. Differing left, right behavior. Therefore, that's terrible. Try that again. Therefore, f of x is, does that need a comma? Probably, not continuous at x equals 3. Did I make that statement right here? Oh, yeah, I did. It said it at the very beginning. F of x is not continuous at x equals 1. So it was in that part. So I drew that conclusion based on this condition, that third condition, second condition. All right. So let's now do the last one here, which was at x equals 5. So is the function defined there? Yes. Does the limit exist there? Yes, it's equal to the same number on both sides. However, those two things don't match up. The value of the limit, the value of the limit and the value of the point are not the same. So this time, whenever I write it up, I'm going to write it as a sentence. I'm going to write, so at x equals 5, I might write, say, something like this. Even though f of 5 is defined and the limit as x approaches 5 of f of x exists, f of x is not continuous at x equals 5. And why is that? Because it fails the third condition. Because the limit as x approaches 5 of f of x is not equal to f of 5. So don't put it in layman's terms. Don't say that the value of the function is not equal to the value of the limit. Actually write out the calculus notation. And when we do this, we're on the road to getting a 5 or maybe even a 6 on that AP Calculus exam.